Hello everyone, welcome back to my YouTube channel. So today we are going to solve day 25 problem of this month on LeetCode. Before starting, I want to share some good news with you all. So our channel has finally completed 500 subscribers and it wouldn't have been possible without your support. So I want to thank you all for this, and this is just the beginning. Let's just keep learning, building and growing together. Okay, so now let's get started with today's problem. Problem number 2845. Count of interesting subarrays. You are given a zero indexed integer array nums and an integer modulo and an integer k. Your task is to find the count of subarrays that are interesting. Okay, a subarray nums L to R is interesting if the following condition holds. Let count be the number of indices I in the range L to R such that nums of I modulo, okay, is equal to k. Okay, so nums of I mod modulo is equal to k. Then the count, which is nothing but the number of indices I, okay, in this range where this condition is satisfied. Okay, so that count mod modulo, it should also be equal to k. Okay, and we have to return an integer denoting the count of interesting subarrays. Okay, so a subarray is a contiguous non-empty sequence of elements within an array. Okay, so let's first understand this line with an example here. Okay, so here see, this is my nums array 3 to 4. Modulo value is 2. Okay, k is equal to 1. All right, so here in this case, if I just pick this element, okay, this just 3, okay, this subarray if I pick, so here this is only number, right, at index 0. So nums of 0 modulus with this modulo. Okay, so here element is 3, mod with modulo value is 2. Okay, so what is the result I am getting? I am getting 1. Okay, and this one value, it is equal to k value. Okay, this k value. All right, so in this subarray there is just one element in which this condition is satisfied. This condition, okay, the condition here, see in white. Okay, this condition is satisfied, only one. Okay, and one is nothing but count. Okay, this is going to be count. So now if I do count mod with modulo, that is 1, mod with modulo 2, so again I am getting 1, okay, which is equal to this k, right? So that simply means that this is an interesting subarray. Okay, so subarray nums 0 to 0, which is 3. There is only one index, that is I is equal to 0 in the range 0 to 0, that satisfies nums of I modulo this modulo equal to k. Okay, so hence count is equal to 1 and count mod modulo is also equal to k. Okay, this is one valid. Now if you take this subarray 3 to, okay, so in this only valid number is this 3. Okay, so count is going to be 1. Okay, valid number means that here if you do 3 modulo with this value, okay, 3 mod with this 2, you are going to get value equal to 1, right, which is equal to k, right? But here if you do 2 mod with the modulo, okay, you are going to get 0, which is not equal to k, so only 1 is valid. So again here 1 mod with again modulo you will do, then again you are going to get k. Okay, so this is also interesting, right? Interesting subarray, right? There is only one index I is equal to 0 in the range 0 to 1, that satisfies nums of I mod modulo is equal to k, hence count is equal to 1 and count mod modulo is equal to k. Okay, now this complete subarray, if you take the subarray nums 0 to, which is 3 to 4, there is only one index I is equal to 0 in the range 0 to 2, that satisfies nums of I mod modulo is equal to k, hence count is equal to 1 and count mod modulo is equal to k. So only these three are possible, right? Okay, so I hope that you guys are clear with this problem statement and example. Okay, now same way here, example number 2. Here in this case, see, if you just pick this subarray. Okay, so here 1 mod with modulo 3. Okay, so here I'm talking about a remainder. Okay, so 3 0. Okay, here 0, so remainder is coming as 1. Okay, remainder is coming as 1 here. Okay, 1 modulo with this 3, remainder is coming as 1. Okay, so here now this is not equal to k, right? This is not equal to k, right? So here tell me how many valid number of counts which are valid. Okay, valid numbers, so 0. Okay, 0 is nice, but the count, okay, zeros are valid. Okay, now here if I do 0 modulo with the 3, I am getting value equal to k. Okay, k is nothing but 0. All right, so here if you see this example here, the subarray nums 1 to 1, which is just 1. Okay, there is no index I in the range 1 to 1, that satisfies this nums of I modulo mod with modulo is equal to k. Okay, there is no, right? So 0, count is 0. So now hence count is 0 and count mode modulo is also equal to k. Okay, done. So this is 1. Okay, this is 1. All right, now here if you pick this complete subarray, okay, which is 3196, so here there are 3 indices I0 to 3 in the range 0 to 3 that satisfies this condition. Okay, so in this there was none, so 0, but when I did 0 modulo with this mode, okay, this value 3, so I was getting 0. Okay, so this was valid, right? So here in this case there are 3, right? This 3 is completely divisible by 3, this 9 is completely divisible by this 3, this 6 is completely divisible by 3, leaving remainder as 0 always, right? Okay, equal to k, right? So count is 3, and now this 3 count mode with this modulo 3, I am again getting value equal to k, so this is also valid. Okay, so it can be shown that there are no other interesting subarrays. Okay, so this is important. Okay, this is important, and this is also interesting. Okay, because in this subarray there are 0, and when I do 0 mode with this modular value, I was getting equal to k again. Okay, so this is also one important boundary condition that we need to check. Okay, and here the constant size is very large. Okay, so definitely I'm not going to iterate like start from here to here, then start from here to here again and again. I'm checking. Okay, so that's not I'm going to do. Okay, otherwise I will get time limit exceed error definitely for this particular problem. Okay, it's very big, right? So now how we are going to solve this problem? Okay, so let's understand that. Okay, so here first we have given an array nums, right, and integer modulo and k. Okay, so let's suppose if the element x in the sub array, okay, so here let's suppose this is my nums array from L to R. Okay, and let's suppose there is an element x. Okay, there is an element x in the sub array. Okay, this nums L to R that satisfies this x mod, okay, and modulo. Okay, modulo modulo equal to k. Okay, so let's suppose this element x satisfies this condition. Okay, so and it appears, let's say, count number of times. Okay, this x appears count number of times, count number of times. Okay, then the subarray nums L to R is called an interesting array. Okay, all right. Okay, so this is done. Interesting array if count again here count modulo mode with modulo equal to k. Okay, so I hope that this line is clear. Okay, so here what I'm saying, we have given an array nums, okay, an integer modulo, all right, and k. Okay, so let's suppose that there is an element x in the subarray nums L to R that satisfies this condition x mod modulo equal to k. Okay, and it appears, let's suppose, count number of times. Now this is going to be an interesting array if and only if count mode with modulo if I do and I get value equal to k. Okay, so this is nothing but this is what we need to do. Okay, for interesting subarray. Okay, now since here see we need to count the number of occurrences of special elements in the array element. Okay, so let's say this is nothing but special elements, special elements. All right, so now since we need to count the number of occurrences of special elements in the array interval, we can consider using prefix sums. Okay, so here let's suppose sums of I is the number of special elements that satisfies x mod modulo k in the array nums from 0 to I. Okay, so let's suppose this is my nums array. Okay, 0 to I. Okay, and here sums of I is nothing but, okay, it's nothing but the number of special elements that satisfies what x mod modulo. Okay, so here we are going to get deep inside some mathematical concepts. Okay, so that's why I'm writing here, so which satisfies this x mod modulo equal to k. Okay, in the arrays nums starting from 0 to I. Okay, sums of I. Okay, so sums of I, what I'm saying here is the number of special elements. Okay, number of special elements that satisfies this x mod modulo equal to k in the array nums from 0 to I. Okay, then the number of special elements in the sub array L to R. Okay, L to R is that is we are going to define that as, let's suppose here until here. Okay, let's suppose this is L, and here let's suppose instead of I you can say R. So here let's suppose it's like R. Okay, so L to R you need to find. Okay, so sums of R is nothing but the number of special elements starting from 0 to R which satisfies this X mod modulo equal to K. And now we want to find this range. So here I can write it like this now. I can write it like this: sums of, okay, R minus, here this is complete, so I can subtract until here now 0 to L minus 1. Okay, so here I can write sums, here I can write L minus 1. Okay, so here's that simply means now from this I am subtracting this part, so definitely I will get this part, that is nothing but L to R. So I can write it like this, right? So this sums of R is nothing but the special numbers which satisfies this condition. Now this sums R minus sums of L minus 1 is nothing but the special numbers, okay, which satisfies this condition. Okay, so this mod modulo equal to K. Okay, okay, so here this X was nothing but this complete sums of R, right? And here for this I can write it like this: sums of R minus sums of L minus 1. So this is nothing but the number of special numbers. Okay, so you can say special numbers in this range L to R which satisfies this condition: special numbers mod modulo equal to K. That is, this is nothing but the count. Okay, count. Done. Okay, now is there any other way to write this same equation? Okay, so let's understand this. Okay, so first let's go over this first. Okay, so by definition of modulus, the expression a mod b, we are going to write, okay, this like this: a is equal to bq plus r. Okay, so here this now see mod with modulo we are doing. Okay, so we are doing this number mod with this modulo equal to k. Okay, so here this is the definition of modulus. Okay, so expression is, let's say, a mod b is equal to r, means that when you divide a by b, the remainder is r. Okay, so this equation, what does this equation simply means? It means that when you divide a by b, the remainder is r. Okay, so you are going to write it like this: a is equal to bq plus r. So a is nothing but the dividend, b is nothing but the divisor, q is nothing but the quotient, and r is the remainder. Okay, so now let me prove this. Okay, let me prove this. So see this example. So here if I ask you guys about this 17 mod, okay, mod and same premise, here you can write it like this now: mod 5. So tell me the remainder. So this is nothing but your a value dividend. Okay, this is nothing but the divisor. Okay, and the remainder is going to be here 17 divided with 5, 5 3 are 15. Here remainder is 2. Okay, so 2 is the remainder. Okay, 2 is the remainder, and here this q is nothing but the quotient. Okay, this is nothing but quotient. Okay, so here this equation, okay, this equation, that is nothing but a mod with b equal to r. I can write this same equation like this. Here just place this a here, a value is 17. Okay, in this equation b is nothing but 5, and q is the quotient. Okay, 5 8 3 plus r is 2. Okay, so here I prove this. Okay, that we can write a mod b like this. Okay, so 17 is equal to 5 into 3 15 plus 2 17. Okay, so LHS is equal to RHS. Okay, so by definition of modulus, the expression a mod b is equal to r means that when you divide a by b, the remainder is r. Formally a is equal to bq plus r. Okay, so this is one important point. Okay, I'm going to use this in this formula. Okay, this thing. All right. Okay, now here there is one more thing. Okay, so here see here, a plus b dot m mod m is equal to a mod m. Okay, so here what I'm doing, so here we have write a mod m. Okay, a plus b. Okay, this, let's understand this now. This property shows that by adding any multiple of m to a number a, okay, by adding, okay, by adding, so here we are doing addition, plus, okay, by adding any multiple of m. So b dot m, definitely this is going to be divisible by m. Okay, b dot m, so any multiple of m to a number a doesn't change the result of a mod m. Okay, so here see, b dot m is divisible by m, so it doesn't affect the remainder. So you are essentially adding a number that contributes 0 to the remainder. So mathematical justification: x is equal to a plus b dot m. Okay, so here in the both side if you add mod m, so here you are going to write this. Okay, so then this is going to become a dot mod m. Okay, so x, let's suppose your x value is a plus b dot m. Okay, so you place this x value, which is nothing but here. Okay, a plus b dot m mod m. Okay, so this is nothing but this a mod m. All right, so here let me prove it with example. Okay, A is 7, B is 3, okay, M is 5. Okay, so here see 7 plus uh, 3 dot 5. Okay, you are putting A plus B dot M, and then you are doing mod with M. Okay, so this equation, so 7 plus 15, here 15 is coming, okay, plus, okay, so you are going to get 2. Okay, now here from this example just remove this part, okay, B dot M. Okay, so just write 7 mod M. So this is also 7 mod M, this is also equal to 2 now, right? Both LHS and RHS matching, right? So this is also one property. Okay, this property shows that adding any multiple of M to a number A doesn't change the result of A mod M. Okay, so now after this we are here now. So this is our original modular equation. Okay, so sums of R minus sums of L minus 1 mod modulo is equal to K. Okay, mod modulo equal to K. Okay, so here I'm taking M. Okay, mod M. So here is modulo, so let's say this is M. Okay, whatever naming convention you can give. Okay, no issues. So this, okay, so by definition of modulus, this means I can write it like this. Okay, sums of R minus sums of L minus 1, and here Q dot M plus K. Okay, so here what is the formula that I'm using? So A mod B equal to K, so I can write it like this. A is equal to uh, your value. Okay, so from here what value is coming? So B Q plus K, this is the, okay, so here Q is extra quotient, and this B is coming from here, okay, which is nothing but divisor. Okay, so this formula A mod B is equal to R, so I'm using this formula A is equal to PQ plus R. Okay, this formula I'm using here. Done. So we can also here do one thing. Okay, so this sums of L minus 1 we can take over to the this side. Okay, so this is going to become positive, and here K is going to come here, so this is going to become like this: sums of R minus K, sums of L minus 1 plus Q1. Okay, now take both sides modulo M. Okay, so here this side add mod M, and this side also add mod M. Okay, done, no change. Okay, now here see this equation: A plus B dot M mod M is equal to A mod M. So we already know this, so I prove this equation here, right? So I prove this equation here. Okay, so if I apply this formula, so I can write this like this. Okay, so here I can remove this Q dot M. Okay, because this is a multiple of M. Okay, divisible by M properly, right? So here I can write this same thing: sums of R minus K mod M, complete left side, and here I can remove this part. Okay, because I already know that A plus B dot M mod M is equal to A mod M. Okay, so from here I can just write sums of L minus 1 and mod M. Okay, I can drive this. So this is done. Okay, this is done. So I'm just changing this equation, rewriting this equation. Okay, now here sometimes this sums of R minus A could be negative. Okay, to safely take a modulus in programmings like Java, Python, or C++, etc., we add M, okay, before taking the modulo to make it a non-negative. Okay, so whatever the value here, just add plus M mod M, so it is not going to create any impact. Okay, so here let's suppose 17 uh, 5. Okay, so remainder is 5 3 15 2. Okay, now in this 17 if you add again M value, okay, M value, so if you add M, so let's say you have added 5 again, okay, this 5, so you are going to get 22. Okay, so now 22 again, if you do it with the 5, so here see there is no change in the remainder, again you are getting 2 remainder. Okay, so that's the reason, okay, we can do this, okay, to make it positive. Okay, so maybe sometimes the integer was negative. Okay, so we are going to do that. All right, so this version is safe for implementation, especially in code. So the conclusion is sums of R minus sums of L minus 1 mod mk. Okay, this was the original that from here we started now, so we can write it like this: sums of R minus K plus M mod M, sums of L minus 1 mod M. Okay, we can write it like this. Okay, now here, now understand this, this is also important point. Okay, so much maths here. All right, so according to the above formula, it can be shown that for index R, okay, index R, if there exists an index L such that L is less than equal to R, and which satisfies this sums of R minus K plus modulo mod modulo, okay, this part LHS is equal to this right part, okay, sums of L minus 1 mod M, then the subarray nums of L to R is an interesting subarray. Okay, so this is the equation that we derived. Okay, so for all the values, okay, where L is less than equal to R and which satisfies this condition, So that simply means that's particular subarray L to R is an interesting array. Okay, so if we place L and R values here and both the sides are equal, okay, so we are going to get interesting subarray. Okay, so now here what does this mean? Okay, so this I can write it as prefix sum. Okay, prefix sum at my current index, prefix sum at my current index of R. Okay, so here let's suppose I am here at R, so until R what was the prefix sum. Okay, and here L minus 1 simply means that previous until here. Okay, previous prefix sum, I can say previous prefix sum. Okay, so previous prefix and sum. Okay, so until here L minus 1. Okay, until here that simply means this is the right side boundary, this is the left side boundary, you can say. Okay, so L is nothing but the left side boundary, na? So until here from where we start. Okay, so let me just go over this in detail. Okay, why I'm saying this previous prefix sum and prefix sum. Okay, so let's go over that. So I hope that you guys are clear with this first. According to our formula, it can be known that for index R, if there exists an index L such that L is less than or equal to R, and which satisfies this condition, then the subarray is going to be interesting subarray. Okay, this is done. Now next point. We are going to use a hash table count to store the number of occurrences of sums of I mod modulo. Okay, in the current prefix that has been traversed. Okay, each time we enumerate the index R from small to large, we expect to be able to quickly find the number of interesting subarrays with R as the right endpoint. Okay, that is the number of left boundaries L that satisfies the condition. Okay, so this right side boundary we know, okay, ending at R, this is going to give me the number of boundaries in the left side which satisfy the condition. Okay, this is going to give me the number of boundaries which are ending at the right endpoint. Okay, and this is going to give me the number of boundaries starting from this left index which are going to satisfy this condition. I'm saying number of boundaries in left side which is going to satisfy this condition. Okay, this is what we need to do, right? So here we expect to be able to quickly find the number of interesting subarrays with R as a right endpoint. That is the number of left boundaries L that satisfy the condition. Okay, so according to above inference, it can be shown that at this time it is only necessary to find the number of elements equal to this. Okay, in the hash table. Okay, number of elements which are equal to this in the hash table count. Okay, and count is going to keep track of the previous prefix sums. Okay, the left side boundaries. Okay, so this is going to be nothing but my required modulo, and this required modulo I'm going to search in the my count hash table which is going to store these values. Okay, required modulo I can say. Okay, so when I'm going to write code, then you guys will get much better understanding, but just understand what is happening here. According to the above inference, it can be known that at this time it is only necessary to find the number of elements equal to this in the hash table count. Okay, count contains the previous valid special numbers. Okay, which is the number of elements satisfying the left boundary condition. We have to add this to the result and finally return the total accumulated result. To optimize the calculation, the prefix sum of the special elements can be represented by a single variable prefix at this time. Okay, so here in layman terms, what I'm saying in layman terms, in easy terms, okay, for each index R, you can count how many valid startings from L exist such that the number of interesting elements in the subarray nums of L to R leaves a remainder of K when divided by modulo M. Okay, so this is the main line, okay, which we are actually doing. Okay, so now let me prove this with an example here, what is going to happen. Okay, so this is nothing but your example number 2, okay, of this particular problem. All right, so this is my nums array, this is modulo, and this is K value. Okay, so N is nothing but the size of the list nums. Count is the hash map to create track of the frequency of each prefix sum modulo. Okay, so here in the initially subarray is empty. Okay, so definitely your prefix sum is going to be 0 in the starting. Okay, so here count is the hash map to keep track of the frequency of each prefix sum modulo mode. So 0. Okay, so here 0 is occurring one time now. So here what I'm going to initialize count output 0 to 1. This means that there is one subarray that gives a remainder of 0, the empty subarray initially. Okay, this is always going to give me the 0 value. Okay, this means that this subarray that is going to give the remainder of 0. Okay, so result I'm going to take create one variable and going to take create one variable prefix. Okay, result is going to store the result number of interesting subarrays, and prefix 0 is to keep track of the prefix sum modulo. Okay, so here what we need to do, let's understand with an example. Okay, this 3196. Okay, 3196. All right. Okay, so 3196, this example. Okay, output is 2. All right, so now here prefix is 0 initially, count is 0 to 1. We start with this because an empty prefix 0 is valid. Okay, empty prefix is also valid, right? Okay, and result is equal to 0 initially. Okay, so now here we are at this particular position. Okay, my I is at this particular position. Okay, nums of 0 value is 3. Now here nums of 0 modulus with 3 I did. Okay, and I get 0, which is equal to k value. Okay, so that simply means that this is a special number. Okay, matches k. So what I'm going to do, I'm going to increment the prefix to 1. Okay, so my prefix is going to become 1 here. Then now this I know which is ending at this right boundary. Okay, so now I want to this is my required modulo. Okay, now I have to find the required modulo. Okay, so here I discuss about this required modulo. Okay, so we expect to able to quickly find the number of interesting subarray with r as a ending right endpoint. Okay, the number of left boundaries that satisfy the condition. Okay, so now we have to find the left boundary that satisfies this condition. Okay, so what I'm going to do here, required modulo, I'm going to write it as like this: prefix, okay, minus k, okay, previous to this, so I'm not going to count this. Okay, prefix minus k, okay, plus modulo, okay, so that we don't get negative value. Okay, so I will do that. So prefix is 1. From this one I am subtracting 0 plus here modulo is value, modulo value is nothing but 3. Okay, 1 minus 0 plus 3. Okay, and then again modulo with 3 I will get 1. Okay, so required modulo is nothing but 1. 1 is nothing but the required modulo that we want to find. Okay, so here previously here, okay, previous prefix sums, so in the count map, okay, so we have only 0 equal to 1, we don't have this one. Okay, we don't have this modulo previously. Okay, so this in this boundary I'm getting the prefix sum as 1. Okay, so in the this right side, okay, which is nothing but l minus 1, which I'm doing here, also I'm searching for that now. Here also I'm searching for this. Okay, because I want to compare these two. Okay, both should be matching. Okay, so this is not there, this is not there. Okay, so what I'm going to do, my result will not be updated, and now after that I will update my count. So 0 I see one time, and this one here I see one time. Okay, so that is why I'm updating it here. Okay, and result value is still 0. Okay, now see this iteration 2. Okay, 3196, 3196, my I is at this particular position. Okay, so now here current number is this equal to 1. Okay, which is not equal to k, k is 0, right? So prefix is going to remain 1. Okay, so until here prefix is going to remain 1. Okay, until here. All right, ending at this. All right, now required modulo is 1 minus 0 plus 3 mod 3 equal to 1. Okay, 1 is the required modulo. So in this until here I'm getting 1, so my required modulo is also 1. Okay, so current count is this 0 and 1, so 1 occurs in my previous hash map. Okay, 1 occurs. All right, okay, so here 1 occurs, so in the result I'm going to get, so see, ending at here. Okay, and we know until here. Okay, so right, this 1 occurs here now, until here this 1 occurs, and here also 1 occurs. Okay, until here, so that means that this is one valid subarray l minus r minus l. Okay, this is valid. So until here my prefix sum is 1. Okay, that is nothing but the right side boundary, and now I want to find the left side boundary, how many valid are there. So until here 3 occurs here now, so in this range we have to find out now. So that's simply, if you take this example 1, okay, ending at this one, okay, and starting from this. Okay, so this is going to be the left boundary until here. Okay, so here result is going to count out get or default, 1 is already there. Okay, one time, so in the result I'm going to add 1. So 0 plus 1, result is going to become 1. And now here I will update the count. Okay, count is nothing but prefix modulus with 3, so prefix is still 1. Okay, so here 1 I am going to update to 2, and 0 is going to remain 1 only. Okay, this is done. Now iteration 3. Okay, I is equal to nums of 2 is equal to 9. Okay, 3196, 3196. Okay, so here this matches k. Okay, so prefix sum is going to be update. Okay, it's going to become 2. So now what, until here, okay, until here, okay, ending at this right side boundary, my required modulo, I'm searching for 2 in the left side. Okay, in the left, how many conditions which satisfy this same required modulo. So in the left side there is no value of 2. Okay, so nothing, right, because we need LHS equal to RHS, right? So here we need this na RHS equal to LHS, LHS equal to RHS. Okay, so here there is nothing. Okay, 2 is not there, so my there will be no impact on the result. Okay, so this is not a valid, so result is going to remain 1 only, right? And now count. Okay, so in the count current prefix value is 2, 2 modulus with 3, you are going to get 2 modulus with 3, you are going to get 2 remainder. Okay, so you are going to add 2 1. All right. Okay. So this prefix, okay, so there are two values which are in special no numbers. Okay, this 3 and 9 special because they are completely divisible by mode value, modulo value. Now see here iteration 4. Okay, 3196. All right. So now here, okay, until here your I reaches here. So here this 6 k, okay, prefix is going to become 3 here. Until here prefix is 3. Okay, now your required modulo is what? Your required modulo is 0. Okay, because here until here, okay, prefix is becoming this. Okay, so what is the modulo that you required? Okay, so here we are applying this formula na? Sums of I minus r plus k, okay, mod m, this side formula. So this is but the right side boundary formula. So in this formula, if you see, we are getting a required modulo as 0. Okay, right. Now in the left side, when we see the 0 last time, okay, when we see the 0 last time, so we see the 0 last time until here. Okay, 0 was one time here. Okay, so in the result we are going to get count or get to default result is equal to 1 plus 1 2. Okay, so here this 0 occurring one time. Okay, so in the result I'm going to add 2, so that simply means that this is a one valid, complete one valid. Okay, until here we know, right? So here one more thing, okay, so let's suppose this until here complete, we know that 3 is a prefix sum until here. Okay, now here last time this 3 is occurring here. Okay, this 3 is occurring here. Okay, prefix sum, but required is nothing but 3 modulo 0. Okay, this formula 3 minus 0, 3 minus 0 plus 3 modulo with mod. Okay, so 3 minus 3. Okay, so you are going to get 0. Okay, so required is 0 and 0 is here last time. Okay, 0 is here until here. Okay, until here, so this is a valid. Okay, so we are incrementing this count. Okay, now here you see that 0 frequency is just 1. Okay, but if 0 frequency is 2, we see 0 2 times. Okay, here, and 0 is also here also. Okay, 0 here, then we are going to add 2 here instead of 1. Okay, previous value of result is 1 and here we are going to just get the value now. Here if it is 2, so we are going to add 2 in that case, right? We are going to add 2. So why 2? So see here, then this is going to be one valid. Okay, L2R, and this is also going to be one valid L2R. So that's the reason. Okay, so this you guys will get much understanding with the code is going to be very simple. Okay, for this one, so just little bit maths is there, right? So instead of coding, this problem is more related to mathematics. Okay, so that's why let's study maths first. Okay, now let's write the code for this. Code is going to be very small for this problem, it's not big. Okay, only few lines of code. Okay, so we are using prefix sum, so definitely we are going to solve this problem of n time complexity. Okay, since we are only iterating the right pointer, okay, and searching for that value in the left which is validating that. Okay, so this, okay, where is that? Okay, this simply, if I give you some example, so in the right side you know that 3 toffees are there. Okay, 3 toffees are there. So in the left bag also you want to find 3 toffees now. So this is what actually you are doing. Okay, so let's write the code. All right, so here int n is equal to nums dot size. Okay, then you have to create one hash map. Okay, map, and key as integer, values as integer, and here let's take name as count is equal to new hash map. Okay, and then here since output that we have to return it should be in long format, so here I'm taking long variable. Okay, long result is equal to 0, and here prefix sum initially is 0 for an empty subarray, and then in the map just update this. Okay, count dot put, and how many times we see this prefix 0? We, as of now, just one time. Okay, so that's the reason. So now here just run one loop. Okay, for int I is equal to 0, I is less than n, and here I plus plus, and inside this what you need to do, first you have to calculate the prefix. Okay, so prefix you are going to update as prefix is prefix plus nums. Okay, this is list nums dot get I, okay, get that particular element and check whether it is special or not. So how you are going to check the special? Mode with the modulo value, okay, which is given to us. If it is equal to k, okay, then take, okay, if it's matching, then increment the prefix sum by 1, otherwise take the 0. Okay, so mode modulo, okay, little bit confusing, so you can use some other terms. You can say xyz, okay, whatever. Modulo, mode modulo is confusing. Mode modulo, okay, so you can take any other variable. Yeah, you can change the function. Okay, here okay, so if for understanding purpose you can try that. Okay, if you are getting confused with the mode modulo. Okay, so here after that you are going to update the result. Okay, so result, how you are going to update. Okay, so here first you have to calculate the required sum modulo for an interesting subarray. Okay, so here instead of writing it directly, okay, let me write it like this: int required modulo. So required modulo is going to be first required modulo. Just check the right side, from there you will get the required modulo. Okay, so here how we are going to get the required modulo. So here you have to write this. Here take it as prefix minus k plus m. Okay, so here you can write prefix minus k plus modulo. Okay, we are using modulo here, modulo, and here mode with the modulo. Okay, we don't want to see the negative numbers here. Okay, so I will make them positive. All right, so here what we are doing, we are calculating the required sum modulo for an interesting subarray. Okay, then we have to count this. We have to check if this already required modulo already exists in my map or not. Okay, so here you can say result is equal to result plus in your hash map. Okay, count dot get or default. It is going to check if this particular key is there in my hash map or not. Okay, if it is there, then it is going to take that value. Okay, otherwise it is going to take 0. All right. Okay, then we have to update the count for the current prefix modulo. Okay, so here I just update the count dot put. Okay, and now what is the current prefix? Okay, take the modulo as well, mode modulo. All right, and here inside this count dot get or default, and here prefix mode modulo. Okay, so here check whether that particular prefix is already there or not. So prefix mode modulo we will do. Okay, if it is already there, then take that particular value, otherwise take 0, and in that particular value just add 1. Okay, we are going to update the count map. Okay, frequency map of particular keys. Okay, and in the end you have to just simply return the result. That's it. Okay, now let's run the code and see if there any code issue. We'll try to fix that. So see, all the test cases has been accepted, right? Now let's submit it. So see, our solution is accepted, right? So I hope that you guys are able to understand today's problem, and if you guys still have any doubts, then please feel free to ask in comment section. Till then, keep coding and keep practicing. Meet you guys in the next video. Thank you. Bye bye.